I have always, can everyone see my screen?
Yeah.
Perfect. Okay. So Dr. Richard was mentioning something about the application of IRIS spectroscopy in quantitative metabolomics. Now, me being an organic chemist, I had extensive experience and knowledge about this, but I have always used this as a qualitative tool. So I thought maybe I'll just dig into the literature and see what's out there and its application, like the application of this spectroscopy to quantify metabolites. So that's going to be my topic today. It's basically going to be in three parts. The beginning portion is just to give a brief overview of what IRIS spectroscopy is, which all of us kind of know. In the second portion, which is very brief actually, is where I'll be highlighting a few out of many examples in the literature where IRIS spectroscopy independently was used in quantitative metabolomics. And the major part of my talk today will be focused on IRIS spectroscopy in combination with other techniques and its application in the field of metabolomics. Oops. Okay, so what is IRIS spectroscopy? I just put a picture of this electromagnetic radiation spectrum over here for better understanding. So it's basically lower energy than red light. The wavelength is basically from 700 nanometer to about 10 to the power 6 nanometer. That's our IR region. And what's the significance of this IR spectroscopy? So basically, chemical bonds can absorb IR radiations. If you look at the picture at the bottom, I depicted a chemical bond. It's like two balls attached with a spring kind of scenario. If a chemical bond absorbs IR radiation, it gets stretched to an excited state, and then it relaxes back to the ground state, releases the energy, and which is being detected by the detector, and you get a specific spectrum for a specific chemical bond. So basically, every chemical bond will absorb IR radiation, and will go to an excited vibrational state, and then you'll get a characteristic peak. The energy transition follows the standard Planck's equation, E, which is energy equals to h nu. H is the Planck's constant, and nu is the frequency. Nu is equal to c by lambda. C is the speed of light, lambda is the wavelength, and 1 by lambda is nu bar, or wave number. And that's the usual thing for to use in IR, and the unit is centimeter inverse, because it's in like 1 by lambda, which is a length, right? And the mid IR is the most important one. So from 4,000 to 400 centimeter inverse, that's the window where most of the chemical bonds will absorb IR radiation to cause vibrations. Now, let us look briefly about some of the molecular vibrations, which are important. So I basically copied this portion from Wikipedia because they have a very nice pictorial depiction. The most important vibration in the world of chemistry is the stretching. That requires the most amount of energy. And there are two types of stretching, as you can see in the picture, symmetric and antisymmetric. And every functional group has its own characteristic stretching frequency, or nu bar. And obviously, if the bond is stronger, you're going to have a higher stretching frequency, and every functional group will have its characteristic position. One very important thing to remember when we're discussing about IR spectroscopy that a lot of people actually overlook is only polar bonds and polar molecules are sensitive towards IR spectroscopy. Molecules that have a permanent dipole moment. Now, you might have a couple of polar bonds in a molecule, like for example, CCl4, carbon tetrachloride. It has 4 carbon-chlorine bonds, each of them are polar, but overall the molecule has no dipole moment. You're not going to see any IR spectrum for such molecules. You need to have a permanent dipole moment. Now, apart from stretching, which of course is the most important one, there are several other types of molecular vibrations, scissoring, rocking, wagging, and twisting, less important. So as organic chemists, we don't really care about those, but in metabolomics, when I'll show you the examples, you will see that those might be important. Just a side note, since I mentioned that the polar molecules will be sensitive towards IR, what if you get a non-polar molecule like carbon dioxide, for example? You have to do something called Raman spectroscopy. So that's the famous work by Indian physicist C.V. Raman. which led him to win the Nobel Prize in chemistry back in 1930, his work on Raman scattering. I actually did my BSc from the same university where he did his work from, University of Calcutta. And I actually saw his lab. It's kind of locked now, it's very old, where he actually discovered his famous Raman scattering. Fun fact for C.V. Raman, he did not have a PhD, formal PhD in his field. Anyway, coming back to our IR spectroscopy thing, as I said, like every molecule and every functional group will have their own characteristic IR spectra. So let us look at some of the important functional groups and how they look on an IR spectrum. So I took this example of benzyl alcohol here. Now, if you note here, there is a blue dotted line on the spectrum at 1400 centimeter inverse. So anything below that energy level is called fingerprint region. That's where all these less important molecular vibrations like wagging or scissoring and stuff like that will show up. The stretchings or some of the overtones will show up the higher energies above 1400 centimeter inverse. So in this picture, you can see the hydroxyl stretching at 3300 broad peak, CH around 3000, a specific appearance of aromatic groups called aromatic overtones around 2200. And also you could see C double bond C around 1500. Let's take another look of another functional group. We have a primary amine here. You'll see a doublet kind of appearance at around 3300. So this typical appearance for a primary amine. I also chose carboxylic acids, very common functional group. So you'll see a very broad peak starting from 3500 all the way going to 2200. And that's the hydroxyl peak of the carboxylic acid. And you will see some sharp spikes, which are the CH of the benzene ring. And you'll also see a very strong, unique, intense peak at 1700 centimeter inverse. That's for the carbonyl of the carboxylic acid. One last example I have is for this acetylene, some specific appearances that I highlighted here. C triple bond C, that's around 2200. C triple bond C hydrogen, that is around 3300, pretty sharp peak. And C double bond C hydrogen, which is around 3000. Okay, so let us now see how we can, like what's been done in the literature to use this IR spectroscopy in the field of metabolomics. Now, there are some advantages using this technique. Obviously, it's low operating cost. First of all you need to spend money for is the IR machine, and certainly way cheaper than mass spec or NMR machines. And the sample preparation is basically super simple, or practically no sample preparation required. Like I'll show you some examples where live organisms can be actually scanned directly without killing them. Then obviously you're not going to need any skilled technician to do that. Pretty simple process. And also it's going to be high throughput because again, it's a simple process. But there are disadvantages to this technique. The most common ones that are reported in the literature are low accuracy and reproducibility. And then also I noticed that most of the metabolites that they have measured, they're of high concentrations. Obviously, when you are determining low concentrations, there will be more interferences. Now I selected 3 representative examples out of many. The first one that I want to talk about is where they were using the near infrared to scan Drosophila flies live. And they were using a chemometric approach to like using a multivariate calibration model to quantify the amount of triglycerides present in the flies. They generated the calibration curve by plotting the IR absorbances against the actual concentration of the metabolite. Now, for determination of the actual concentration, they used an Abcam kit. But unfortunately, they reported a correlation of the actual versus observed is only up to 0.7. So it's not really a great example. The second one that I saw in the literature is pretty common, is the non-invasive measurement of blood glucose level. So basically scan one portion of your skin with the IR machine to actually quantify blood glucose level. The obvious interference is going to be water, protein, or fat present in the tissue. Lots of literature, most of them like suggested that there are sensitivity or reproducibility issues. But there was one literature where they used this technique in the range of 1050 to 2450 nanometer. And that showed a pretty good result. And the error was less than 10% for quantification of glucose. And the last example where IR is used by itself was where there was an invasive technique. So they actually scan, like analyze the blood samples, human blood samples, to quantify lactate. They also use near infrared and 2050 to 2400 nanometer. And they got a very good correlation. So 0.98, that's pretty amazing. Of course, the interference are from protein and water, but the water peaks are just below and above their scanning range. So they actually were able to solve that problem. Okay, now switching to my main focus of the topic today is what can we do to use IR in combination with another technique to get great improvements in the metabolomics. Obviously, the best technique known in the world of metabolomics is going to be mass spec because of its high sensitivity and selectivity. So how about we combine mass spec and IR? So I found quite a few literature actually where people have used this technique and they have reached to very nice conclusions and results. So I'll just give you a couple of highlights on that. There is one drawback in mass spec. We all know it's the best, but the main drawback is it cannot predict the molecular structure. And by saying structure, I mean the regiochemistry and stereochemistry. So basically, regiochemistry means where the functional groups are attached to the molecule. And stereochemistry means the three-dimensional orientation of the functional groups. Mass spec does not tell you that. NMR does, but obviously NMR is very sensitive. It's not very sensitive as mass spec is. IR does, because IR is basically a fingerprint of every single molecule. Just to give you an example, if you look at these two structures here, it's a cis-trans isomers of the same thing. Very, very close structures, but you can clearly see the fingerprints, the IR fingerprints are so significantly different. So now what I'm gonna show you is some of the examples where mass spec and IR spectroscopy were combined. The name of this method is called IRIS, or IR ion spectroscopy, which basically gives a fingerprint of the mass isolated ions in the mass spec machine. So what's the difference between a traditional IR and this method? So this IRIS method uses a technique called infra-red multiple photon dissociation, or IRMPD, which was established back in 1981. Now, what it basically does is there is an IR laser, and the IR light is passed through those ions which are trapped in the vacuum of the mass spec. And basically, the ions will absorb the IR radiation, will go to the higher excited state, and then eventually they'll fragment. If you think of the traditional IR spectroscopy, we don't do such things. We basically let the IR light go through the molecules, and the molecule will jump into the excited vibrational state, and then we measure the reduction in the signal intensity to understand which IR absorptions were, like which wavelengths were absorbed. But this technique cannot be done in the mass spec simply because of the low ion density. So they have to use this IRMPD technique, and then the ions will vibrate to the higher excited state, and eventually they'll fragment. And once it generates the IR spectra of those mass isolated ions in the mass spec, then you can compare that with the reference spectra, and you can either use like a commercial standard and accurate the spectra, compare, or you can create a theoretical spectra by calculations and then compare. I'll show you examples of both in my next few slides. Just one quick thing is the traditional CID and IRMPD, their fragmentations are usually similar. So that serves our purpose. But if someone's interested, you can go in the literature. There's a thorough discussion, like a comparative study done between the traditional CID and IRMPD, like what are the differences and stuff. This method is mainly used for ion trap mass spec machines, or the Fourier transform ion cyclotron resonance machine. So this is a picture of the FTICR in our chemistry department at UFA. They used to use this technique with IR lasers a few years back. They don't do it anymore. But yeah, those are the two main machines where you can use this. Now, before jumping into metabolomics examples, I'm just going to show you some of the highlights of this IRIS technique. So the first time a tunable IR laser was used, that was in 2000, where they were acquiring the IR spectra of some hydrocarbons. So as you can see in the picture, the smooth black line represents the theoretical spectrum, and the other one is the actual experimental. And there's a pretty good match to actually tell you that which polyaromatic hydrocarbon is this. So basically, for the tuning, tunable laser, you can just tune the laser to make it go in resonance with the IR allowed transition. So you can actually see which transitions are happening. Now, most of the reports that I found in the literature for this IRIS technique before the application of it in the metabolomics were where they were identifying the metal ion coordination geometries or ion hydration effects or structure of the intermediates or interaction of metals with peptides or dissociation of peptides and things like that. So I just took one representative example from the literature where they're studying this dipeptide coordination with different metal ions. So they choose phenylalanyl, phenylalanine as an example. Two different types of coordination possible. One where the carbonyl can directly coordinate with the metal ion, it's called the charged solvated form. And the other one is the iminol form where the amide actually tautomerizes to the iminol, and then it gets coordinated with the metal through nitrogen. If you look at the picture here, so the red bar actually shows, the red bar basically shows the existence of the amide bond. So it's basically the NH bending of the charged solvated form to the left. And you can see lithium and calcium, they have that peak, but when you're moving on to magnesium, nickel, and cobalt, that peak has disappeared. And you see peak, which is highlighted with the blue bar, and that actually signifies the imminol form. It's basically the OH bending. So this tells you, well, calcium probably shows both to a certain extent, but it actually tells you what type of form of the dipeptide is existing in presence of different metals. Okay, now I'm going to switch to its application in the world of metabolomics. You might, if you're interested, you can read this citation here. It's a pretty good review on a lot of techniques that's been applied. So the first successful application in metabolomics was reported back in 2017 on human samples, where, I mean, actually this picture will explain you how you can actually do this. So they were detecting the N-acetyl manosamine, which is a biomarker for N-acetyl neuraminic acid synthase deficiency, which is a newborn error of metabolism. There are different possible biomarkers that they were not able to distinguish between. So those are the three at the bottom. And so the technique is when they ran the cerebrospinal fluid sample of the patient, they did a mass isolation, which is the molecular ion of 244. And they used different IR lasers, as you can see in this picture. So panel C, actually, if you see that picture, there are two different IR lasers that they used. 1600 centimeter inverse, that was not useful. 1050, that was resonant, and they were able to create the IR spectrum of that mass isolated peak at 244. That's in panel D. Now they matched that with the actual IR spectrum of the three possible metabolites, and you can see blue is a perfect match. So that's how they were able to identify that it was the N-acetyl manosamine. So the good thing about this technique is you didn't need any HPLC on this. You just take the whole chunk, isolate in terms of mass, and perform the IR. And obviously, since it's happening in the mass spec, the sensitivity of this technique is as good as a mass spec sensitivity. Okay. Now I'll show you a couple of more examples where this technique was used, where there was no HPLC required. One such technique here on screen is the regio isomers of prostaglandin, the D2 and E2 versions. They're very difficult to separate in HPLC, and their MSMS fragmentation patterns are also very similar. Definitely not identical, but pretty similar. So it's difficult to distinguish them. So what they did basically is they acquired so let's look at the panel D first. I'll come back to panel C a little later. They acquired the IRIS spectrum of both of them. And you can see for E2, you have one peak at 1750 centimeter inverse in blue, whereas D2 has two characteristic peaks at 1650 and 1700 centimeter inverse. You can actually calculate the relative ratio of the E2 and D2 in an unknown sample. So if you look at the black peak in panel D, that's actually a known sample of 1:1 mixture of both E2 and D2. So you can basically compare the peak heights once you match the spectrum and then calculate the relative ratios. And also, if you now look at panel C, you can clearly see that at 700 centimeter inverse, D2 is actually showing a peak. So you can do something called a two-laser isomer selective IR method, where you can selectively generate IR spectrum of one metabolite in presence of others. So what you need to do here is shine in the IR beam at 710, IR laser at 710, and that will be absorbed by D2 selectively, and it will be destroyed. It will be gone. And then you can use a tunable laser, that's your second laser, to actually create the IR spectrum of E2 selectively. Okay. Now I'll show you an example where HPLC and IRIS were combined. So this is an example of the separation of homogencetic acid, which is a biomarker for alkaptonuria, which is an inborn error of metabolism, and DOPAC, which is basically a dopamine metabolite. They're separable in HPLC, but if you look at their MSMS in panel B, they're basically identical. So you can't differentiate, or you can't tell which one is which. But once you do the IRIS, you will see their IR spectra are so different. DOPAC shows a characteristic peak at 1800 centimeter inverse, whereas homogencetic acid, shows a peak at 1650 centimeter inverse. So clear distinction between them. Now, me being an organic chemist, I thought of throwing in some organic chemistry ideas here to actually explain why you see these two differences. So if you look at the deprotonated version of the homogencetic acid, which is happening in the mass spec, of course, the deprotonation, or the loss of proton, basically happens from the carboxylic acid group on the side chain of homogencetic acid, shown in red. Once that happens, and the question is like, why does it happen from the carboxylic acid group? Because once that happens, it will generate the carboxylate, and then it will have an intramolecular hydrogen bonding with the phenolic hydroxy ortho to it. It's going to be stable. And also, once you generate the carboxylic acid, carboxylate, it's going to be in resonance. So the negative charge is going to be resonating through two oxygens, reducing the strength of the C double bond O. Therefore, the peak is going to show up at 1650 centimeter inverse. If you remember my earlier slides, I said weaker bonds, lower stretching, stronger bonds, higher stretching. So here you have a weaker C double bond O, you get a peak at 1650. If you look at the deprotonated version of the DOPAC, that's going to happen from the phenolic hydroxy, shown in blue. Again, the reason is you have an ortho hydroxy group right next to it to stabilize that conjugate base via intramolecular hydrogen bonding. And therefore, you're basically leaving that carboxylic acid in the side chain alone. That C double bond is going to be stronger. It's going to show up at higher stretching 1800 centimeter inverse. So long story short, basically, you are able to distinguish these two compounds, which have identical MSMS, from this IR-IS spectrum. One more example of HPLC and IRIS combined, that's the metabolism of atorvastatin, which is a drug to treat the abnormal lipid levels. When it's metabolized, it forms the ortho and para-substituted phenols. You can see from this picture, the panel one is basically the para-substituted one, perfect match with the theoretical IRIS spectrum. So you can identify that, that's a green. The blue is basically in panel 2, which is the ortho substituted. And in panel 3, we're just showing the overlap of both of the iris. Very, very different. You can see the MSMS spectra of both ortho and para, they're identical. So again, problem with identification that can be taken care of by iris. I'll show you an example here with of the application of this technique in untargeted analysis. So in this example, so people are performing the LCMS analysis of plasma samples of 2 siblings. They were suffering from neurological disease, and they saw an unknown peak at 100.0757. They did a literature search in the database, and they found quite a few matches. They basically created the theoretical IRIS spectra of all those. They probably had like more than 90 matches, something. Of course, they did not purchase all 90 standards. So they did the theoretical matching. And if you look at the panel D, you'll see that's a pretty good match with N-methylpyrrolidinone. So they purchased that standard and ran the IR spectrum of that specific standard, which is in panel E. You can see that's a perfect match. So this way they were able to identify the unknown. One more example of iris in untargeted, that is the pyridoxine-dependent epilepsy, which is also an inborn error of lysine metabolism. They found an unknown, like 2 unknown peaks at 2.33 and 2.55 minutes in HPLC, both showing a mass of 186.1123. And they both fragmented to 128, which was later on identified as P6C. The structure is shown in the picture to the left. You can actually see this is an overlap of 3 IR spectra. The orange is the theoretical standard of that P6C. The blue is the experimental standard, and the black is actual unknown sample spectrum. And so they identified the 128 peak as P6C. And from there, they were able to identify the 2 diastereomers, as you can see in the picture to the right, by performing the IRIS matching. So cis and trans diastereomers. So far, I showed examples where IRIS was applied to molecular ions. You can also apply this to a fragment. So this is an example here. So they were analyzing the plasma sample of a hyperlysinemia patient, which shows elevated lysine, plasma lysine levels. So you can see panel A, the mass spec, 147, that's lysine, and a fragmentation to 130, which shows the loss of ammonia. Now, if you look at panel B, that's the IRIS spectrum of lysine, and it's not a good match. So although we know it's lysine now, but to confirm that, what they performed is IRIS spectrum on the fragment, 130. And that IRIS matched completely or nicely with pipecolic acid. The structure is shown on panel D. So they knew that the lysine is actually fragmenting to pipecolic acid. And also that showed the mechanism of fragmentation. So you see the alpha amine is actually attacking the side chain amine, which acts as a living group, and then you get the cyclized form. So 130 is not the amine being lost from the alpha position, but it's actually from the side chain. So you actually know the mechanism of fragmentation as well once you do this IRIS. So I'll end my discussion with this last slide over here. It's of significant forensic relevance. So where they were trying to detect the different regioisomers of a controlled substance called MMC, methyl methcathinone. Yeah. So there are 3 possible regioisomers: ortho in blue, meta in green, and para in red. And the mass spec shows identical patterns. So basically, the only way to determine the actual regiochemistry is doing the IRIS, and you can see a pretty good match with the corresponding theoretical IRIS spectra, which are shown in black. Okay, that's everything about my presentation today. I hope to hear some comments, suggestions, questions from the audience. A lot of mass spec experts there, so I'd love to get some comments from you guys. Yeah, and thanks very much for being present in the meeting today. Thank you.
Thanks very much, Dipanjan. Very nice presentation.
Thanks.
And some, I think, really impressive results in seeing what IRIS can do.